We're ready to start section 16.5. You might wonder what happened to 16.4, and the answer is that we have temporarily skipped it. The skipping is temporary. We are going to go back. 16.4 is something called Green's theorem, and I think it's easiest to look at that as a special case of Stokes' theorem, but you have to know Stokes' theorem in order to do that. So we're going to finish this chapter, which ends up with Stokes' theorem, and then we'll take a look at Green's theorem at the end. Okay. So right now we're going to be defining these things called curl and divergence. They are only defined in 3 space for our purposes. So they're both things that apply to vector fields in 3 space. Okay. Some textbooks will modify the definitions and allow you to talk about the curl and the divergence of a vector field in 2 space. Our textbook doesn't. I'm going to go with that. Okay. So curl and divergence, we're definitely in 3 space if we're talking about those things. And they're both defined in terms of this thing called the del operator. Okay. We've sort of seen that before because that's the symbol we put in front of a real valued function if we want to take its gradient. It's the same symbol there. Okay. Before I explain it in greater detail, I want to just remind us or tell us, don't know if this is a reminder or new information, what an operator is. An operator is something where there's an input, which is a function, and an output, which is a function. So sometimes people want to say it's a function that acts on functions. That's not quite right because a function has to have a unique output for every input. And some operators do, but some don't. So an example of an operator would be the derivative operator. If I apply that to a function f of x, I get out a related function f prime of x. Of course, this only acts on functions that happen to be differentiable. Now, that's an operator where each input will have a unique output. A function can have one and only one derivative. However, the integral operator is also an operator. If I apply that, let's say to f prime of x, I would get f of x plus c. So I'm not getting a unique output. Okay. So some operators will give us a unique output, and those are functions whose input and output are functions. Some operators just take us from a function to a family of functions or a group of functions. So those aren't functions of functions, but they're still relations of functions, where I can think of it as it's sort of a machine where you plug in a function, it does something, and spits out a related function. Okay. Let's see. Another good example of an operator would be the partial derivative operators. So all of these are operators where you can plug in a function and you'll get out another function. That's important because the partial derivative operators are actually used in defining del. I can sort of write del as a vector of operators. So the first component is the operator that has me take the partial derivative with respect to x. The second component is the operator that has me take the partial with respect to y. And the third component is what has me take the partial with respect to z. So as I said, we've seen this before when we apply it to real valued functions. So if I had something like f of x, y, z equals x squared yz cubed, and I applied the del operator to that to get del f, that would just give me the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, which of course would just be 2xyz cubed, comma, x squared z cubed, comma, 3x squared yz squared. Okay. So I can apply the operator to a real valued function of 3 variables, and it just gives me the gradient of that function. So that's the context in which we've seen it before. However, I can also use this with vector fields. So let's suppose I have a vector field in 3 space. Now I'm going to just name the component functions. So let's name them f of x, y, z, g of x, y, z, h of x, y, z. Okay, so each of the components is itself a function of 3 variables. I can define the curl of f. Symbolically, we denote it as the del operator crossed with my vector field f. Now, if we take a look at what that would look like, it's a symbolic determinant. Anytime I'm taking a cross product, it's already a symbolic determinant, where in my first row, I put I, j, and k. Now, the del operator, its components are these partials, so partial x, partial y, partial z, and then f, its components are these functions, f, g, h. So this is absolutely a symbolic determinant. This is not a real valued matrix. The first row is vectors, the second row is operators, and the third row is functions. Kind of crazy. But what this is going to do is it's going to give me a vector, because it always gives me some i's, some j's, and some k's. So it's going to give me a vector, and what I do is I replace the notion of multiplying, because I can't multiply an operator by a function. I replace the notion of multiplying with just applying the operator. So when I'm looking for how many i's I would get, so I cross off this row and this column, I'm going to get this diagonal minus that diagonal. I'm getting the partial of h with respect to y minus the partial of g with respect to z. That's the number of i's I would have, so that's the first component of this curl vector. For the j's, I want to remember that this one's negative, so I'm going to do it backwards. So I'm not multiplying, but I'm applying these operators to these functions. So I'm going to get the partial of f with respect to z minus the partial of h with respect to x. And then for the k component, I'm going to just get the determinant of this 2 by 2 matrix, partial of g with respect to x minus partial of f with respect to y. Now, if I had to memorize that derivative, I'd probably find it hopeless. Or that formula, rather. This formula I can remember. So it's a symbolic determinant. Notice the curl of f is now itself a vector field. So it's a vector field that's related to the vector field f. Okay. Each of these are real valued functions of 3 variables, but I've got 3 of them as the components of a vector in 3 space, so the curl of f is itself a vector field. Now, this is the definition of the curl. Okay. What does it mean, and why do we call it curl? It would seem like it would have something to do with how much a vector field is curling or rotating, and it does. And we will eventually see that, okay? Right now, we're just sort of learning the mechanics of what is it and how do I calculate it. So, let's just practice that. Let's suppose my vector field f is x squared y e to the xy z, oh, let's make that z e to the xy, and then z squared x over y. Okay, excellent. So if I want to calculate the curl of f, I know that that's the del operator crossed with f. So I'm going to just write out my symbolic determinant, I, j, k, partial x, partial y, partial z. And then I'm going to just put my component functions in that third row. So x squared y, z e to the xy, z squared x over y. So in my first component, I'm getting this symbolic determinant. So I'm taking the partial with respect to y. I'm just going to do a little bit of side work here. Partial with respect to y of this function, I'm just going to rewrite that as z squared x times y to the negative 1. And that way I can see I'm going to get negative z squared x y to the negative 2, or y squared, minus the partial of this with respect to z is just e to the xy. For the second component, the j's, just want to remember to do it backwards. Now, there aren't any z's in this formula, so the partial with respect to z is just 0, and then I'm subtracting the partial of this with respect to x, which would just be z squared over y. Then for the k's, I'm taking the partial of this with respect to x, so that's going to be z, e to the xy, chain rule, I get an extra factor of y. So we'll have yz, e to the xy, minus the partial of this with respect to y is x squared. So that is our curl. We will eventually see what it means, but for right now we just need to have it defined. When we come back in the next video, I will give you one very significant fact about the curl that does relate to something that we've already covered, and that's conservative vector fields.